We now start the discussions on the second module, module 2 of chapter 9. In the last module, we have introduced two special classes of sets called rings and sigma rings, and we have discussed some of their basic properties. In this module, we are going to further study some related concepts, and more importantly, we are going to introduce another class of sets called monotone class, and we will examine its relation with the notions of rings and sigma rings. We start with the notion of Borel sets, which we had seen in chapter 1. We had told you that we will discuss it in chapter 9. The sigma algebra generated by the collection of all open subsets of the real line is called the class of Borel sets. We are going to prove that if f R to R is a continuous function and B is a Borel set, then f inverse B, that is inverse image of the Borel set, is again a Borel set. Let us denote by script P the Borel sigma algebra over the real line. Let us denote by script C as the collection of all subsets E of R for which f inverse E belongs to script B. Since f is continuous, note that inverse image of an open set is open. So, C contains all open subsets of R. So, we have to show that C is a sigma algebra. For this, we start with a member E from C. Now, f inverse of R minus E is equal to R minus f inverse E, and it belongs to the class B. As the set f inverse E already belongs to the class B and B is a sigma algebra, and so it is closed under complementation. So, E complement equal to R minus E belongs to C. Now, let us take a sequence of sets E k, k belonging to n from C. F inverse of union k equal to 1 to infinity E k, this is equal to union k equal to 1 to infinity f inverse E k, because these operations remain invariant under f inverse, and see that this belongs to B, because every member f inverse E k already belongs to B and B is closed under countable union. This shows that union k equal to 1 to infinity E k also belongs to C. So, we have got our result that C is closed under both complementation and countable union, and hence it is a sigma algebra. Now, C is a sigma algebra containing the class of open sets, and by our definition B is the smallest sigma algebra containing open sets. So, we must have B subset of C. And so, this shows that if we take a Borel set B, then the Borel set B belongs to the class C, but the class C is the set of all those subsets E for which F inverse E belongs to B. So, this proves that F inverse B also belongs to B, and so the inverse image of a Borel set under a continuous mapping is again a Borel set. We now introduce our third definition. A non-empty collection H of subsets of a non-empty set X is called a hereditary sigma ring if it is a sigma ring and is hereditary, that is, whenever A belongs to H and B is subset of A, then B belongs to H. That is, whenever a set belongs to the collection H, all its subsets also belongs to H. We can observe that as in the case of rings and sigma rings, intersections of hereditary sigma rings is again a hereditary sigma ring, and for a class of subsets E, we can define the hereditary sigma ring H E generated by the class E as the smallest hereditary sigma ring containing E, in the same way as we define R E or S E. In particular, if we consider the members of H E, recall that every member of S E had the property that it could be covered by countable number of members from E. Since H E is hereditary, so we can say that H E consists of exactly all those subsets of X which can be covered by a countable number of members of E. Now, we introduce our last definition in this set theoretic classes. A non-empty class of subsets M of a set X is called a monotone class if for any monotonic sequence of sets A n in M, we have the limit set A n belongs to M, where for a monotonically increasing sequence of sets A n, that is when A 1 subset of A 2 subset of A 3 etc., we define the limit set as the union of all the sets, that is union n equal to 1 to infinity A n, and for a monotonically decreasing sequence A 1 containing A 2 containing A 3 etc., we define the limit set as their intersection. Now, we have to understand what is the relation between a ring or sigma ring and a monotone class. First, observe that if we take the collection of all finite subsets of the set of natural numbers, say, it forms a ring, but it is not a monotone class, because singleton set 1 is subset of the set 1 2, subset of 1 2 3. This is an increasing sequence of sets in that ring whose union does not belong to the ring. On the contrary, if we just consider the collection of sets, say singleton set A, singleton set A B, then A B C, then this is a monotone class, but it is not a ring, since it is not closed under difference. So, there is no relation between the notion of a ring and a monotone class. We will now prove that a class of sets S is a sigma ring if and only if it is a monotone class and a ring, that is, it is a monotone ring. Observe that if S is a sigma ring, then it is already a ring. Also, it is a monotone class, because a sigma ring is already closed under countable union as well as countable intersection. Conversely, suppose that S is a monotone ring. Since it is a ring, it is already closed under difference. So, we have to show that it is closed under countable union. For that, let us take a sequence of sets A I belonging to N from S. Now, construct the sets F1, F2, Fn in this way. We take F1 as A1, F2 as A1 union A2, Fn as A1 union A2 union An, and so on. Then evidently this new sequence Fn is monotonically increasing sequence of sets, and every Fn belongs to S. But by our assumption S is a monotone class. So, union n equal to 1 to infinity Fn already belongs to S, but this union is equal to union n equal to 1 to infinity An. So, this shows that S is also closed under countable union, and so S is a sigma ring. So, we have observed that M are subset of S R. Now, we want to show the reverse inclusion, that is S R subset of M R. See that M R already contains R, and M R is by definition a monotone class. If we can show that M R is a ring, then M R becomes a monotone ring and consequently a sigma ring containing R. Since S R is the smallest sigma ring containing R, so this will show that we must have S R subset of M R. So, we need to show that M R is a ring. For F subset of X, let us define a class of sets K F as the collection of all those sets E for which E union F, E minus F and F minus E belongs to M R. Now, see that from the definition it readily follows that E belongs to K F if and only if F belongs to K E. We will now show that this class K F is a monotone class when it is non-empty. We now start the proof. Let n belonging to capital N be a monotonically increasing sequence of sets in Kf. Observe that limit n union f, this is equal to union n union f. This is again equal to union n union f, and this is nothing but limit n union f, which belongs to MR, because union f is again a monotonically increasing sequence of sets. If we consider limit n minus f, then this is equal to union n minus f, which is equal to union n minus f, and this is again equal to limit n minus f, which belongs to MR. Here again the same logic is used, that n is monotonically increasing. So, n minus f, this sequence is also monotonically increasing, and all the sets belongs to MR. Finally, if we consider f minus limit n, then this is equal to f minus union n, which is equal to intersection n f minus n, and this is equal to limit n f minus n belonging to MR. Again observe that as n is increasing, so f minus n is decreasing. So, this shows that the limit set limit n belongs to Kf. Similarly, for a monotonically decreasing sequence of sets from Kf, we can show that the limit set belongs to Kf, and this proves our first observation, that Kf is a monotone class if it is non-empty. Now, we start with two sets E and F from R. Since R is a ring, so see that E minus F, F minus E and E union F, all of them belongs to R. Since R is a ring, and consequently as R is subset of MR, so all the three sets E minus F, F minus E and E union F, they belongs to MR, and this shows that E belongs to Kf. Now, this is true for any E belonging to R. So, we must have R subset of Kf. Again, note that we have already seen that Kf is a monotone class when it is non-empty. In this case, obviously it is non-empty. So, Kf is a monotone class. Again, as Kf is a monotone class, since we have already seen that Kf becomes a monotone class when it is non-empty, and here for f belonging to R, it is obviously non-empty. So, we must have MR subset of Kf. Finally, we take E from the class MR. Now, see that E belongs to Kf, where f belongs to R. and we have already seen that E belongs to Kf is equivalent to saying that F belongs to Ke. So, we have F belongs to Ke. Here E belongs to Mr and F is a member of R. So, again by the same logic, since the above relation is true for any member of R, so R is contained in Ke. And we have already seen that Ke is a monotone class and Mr is the smallest monotone class containing R. So, by the same reasoning we have Mr subset of Ke. Since this is true for all E belonging to Mr, so this shows that for any two members E and F from Mr, we have E minus F, F minus E and E union F again belongs to Mr, and this shows that Mr is closed under both union and difference, and hence Mr becomes a ring, and this completes the proof of our assertion. So, to summarize, what we did in this module is that we have defined a new type of class called monotone class. We had earlier defined two types of classes in the first module, namely ring and a sigma ring. We have examined the relation between a monotone class and a ring and a sigma ring, and finally we have proved that for a ring R, the generated sigma ring Sr is equal to the generated monotone class Mr, and with this we end this module.